So the idea of an image tells you, if you have a subset of the domain, what does it look like when you go forward using a function to the codomain. You could ask a similar question, but in reverse. If you have some subset of the codomain, what happens if you follow the function backwards to the domain? And that gives us the idea of an inverse image. So for a function from a domain to codomain R, if you have a subset of the codomain S, then the inverse image of S is just everything in the domain that the function sends to that subset. And we'll write it this way, f inverse of the set S. By the way, this notation does not imply that f is a one-to-one function. Sorry, it doesn't imply that f is an invertible function. In general, it won't be. So right, you can define inverse image whether the function is invertible or not. So the situation here is, right, again, we have a domain and a codomain. We have this subset S over here in the range. Right? For things in the domain, right, the function is going to map things in the domain over to stuff in the codomain, but many elements in the domain may land outside of S once you go over to the codomain. Only some elements of the domain, in general, will end up inside of S. So the elements that get sent into S, this is the inverse image of S. Right? Maybe an example would be instructive if we look at the function from real numbers to real numbers, defined by, say, f of x equals x squared. Right? What is the inverse image of the single real number 1? Right? This is all of the numbers. So this set 1 lives over here in the codomain. So its inverse image is all the real numbers that get sent to a number in this set. So all the numbers that get sent to 1, but there's 2 of them, 1 and minus 1, right? By a similar token, the inverse image of, say, 0 and 2, well, these are all of the numbers that this function sends to either 0 or 2. Well, there's 0 because f of 0 is 0, and then there's 2 and minus root 2 and plus root 2. Because this function sends both of these to 2, which is in this set. Right? So this is this definition of inverse image works for any function. If our function happens to be a linear map, then something nice happens, which is that if you start with a subspace in your codomain, then the inverse image is actually a subspace of the domain. So kind of similar to the situation with image. So if you have a subspace after the function, you started with a subspace before the function, basically, or the inverse image is a subspace. So how can we check this? So let's let S, a subset of W, be a subspace. Okay, we need to show that the inverse image is a subspace. So how can we show the inverse image is a subspace? Show that it's closed under linear combinations of 2 elements. Right? So let's take 2 things in the inverse image. So say v1 and v2 in the inverse image of S. We need to show that a linear combination of this is also in the inverse image. So let's consider a1 v1 plus a2 v2. So we need to know, is this linear combination in the inverse image? Well, how do you check if something is in the inverse image? It's in the inverse image if, when you hit it with f, you end up in S. So let's see what f of a1 v1 plus a2 v2. So let's see what this is. Well, f is a linear map, so we can use the fact that it preserves structure. So this is equal to a1 f of v1 plus a2 f of v2. But this has to be in S. This is in S because of 2 things. First of all, f of v1 and f of v2 are in S. And this is because V1 and V2 are in the inverse image of S. So right, by definition, this means that if you hit either one of these with F, you end up in S. So right, that's what we're saying right here. But on the other hand, S is a subspace of W. That was one of our assumptions. Since S is a subspace, any linear combination of these two elements in S, right, we know that these are in S, so a linear combination of them also has to be in S, because S is closed under linear combinations because it's a subspace. Right, so what we've shown is that if you take this linear combination of the V's, you hit it with F, you end up in S. But that means that A1V1 plus A2V2 is in the inverse image of S. Right? So the inverse image of S is closed under scalar multiplication and vector addition. So the inverse image of S is a subspace of V. All right. So this is a general fact that if you sort of pull back along a function, if you pull a subspace back to the domain, you get another subspace if the map is a linear map. Of course, there's one particular example of this that's most important. You might think that the most important example is the inverse image of W, the entire codomain, but actually the inverse image of W is always all of V, so that's actually not very interesting. The interesting situation is actually the inverse image of just the zero vector in W. So we have a special name for the inverse image of just the zero vector in W, and we call it the null space of the linear map. So null F for null space. So it's the inverse image of just the zero vector in W. So it's the collection of vectors in V that the linear map sends to the zero vector in W. Because of what we said before, we know that this is a subspace of the domain. Since it's a subspace, we can ask about its dimension, and we'll name the dimension of the null space. The dimension of the null space we'll call the nullity of the function.